All right, next up, I want to look at the solution to Arctic 3, where we're titrating the weak base. This is hydrazine. We have 100 milliliters of H2NNH2, and this is at 0.1 molar. And we are going to titrate this with 0.2 molar nitric acid. So this is a weak base, and this is a strong acid. So the first step here, before any of the strong acid has been added, is to find out what the OH minus ion concentration would be. So hydrazine is a weak base, so it's going to react with water to form this H2NNH3 plus, this conjugate acid, and OH minus. If all we have is our 0.1 molar hydrazine, then we just need to think about what's going to happen here. Our 0.1 molar hydrazine is going to produce this and OH minus. And then this one's going to decrease by a factor X, but we're going to assume that that's real small since K sub B here is 3 times 10 to the minus 6. We'll set that equal to X squared from this times this, and 0.1 minus X. We're going to assume that this X here is real small and just say 0.1. So then solving for X, if we multiply both sides by 0.1, take the square root, we get 5.5 times 10 to the minus 4. That's the same. So this X is our hydroxide ion concentration. So then we're going to say that the POH is equal to the negative log of 5.5 times 10 to the minus 4. That gives us a POH of about 3.26. So pH then is 14 minus 3.26, which is about 10.74. Okay, so then we need to start adding some of the strong base in nitric acid. So first we're going to think about what happens stoichiometrically speaking. So our hydrazine reacts with H plus, comes from nitric acid to form the conjugate acid H2NNH3 plus. So we started with 100 milliliters of 0.1 molar hydrazine. So that's going to be 0.1 times 0.1 is 0.01 moles of this. And with that, we're going to be reacting 20 milliliters of 0.2 molar nitric acid. So that's going to be 0.02 for 20 milliliters times 0.2 for the concentration is 0.004 moles of H plus. So after these react, we're going to have none of the H plus. We're going to have 0.004 of this conjugate base. conjugate acid. And we're going to have 0.1 minus 0.004, 0.01, excuse me, minus 0.004 is going to be 0.006 moles. So here, again, we can use the Henderson-Hasselbalch equation, which says that the pH is equal to the pKa plus the log of the concentration of base over the concentration of acid. But we were only given K sub B for this, and we want to use K sub A. So we can get to K sub A for this conjugate acid by taking K sub W for water, 1 times 10 to the minus 14th, dividing by the K sub B for hydrazine, which is 3 times 10 to the minus 6. Okay, that gives us K sub A of 3.3 times 10 to the minus 9. Okay, so then pH equals negative log of 3.3 times 10 to the minus 9 plus the log of our base concentration. Okay, here hydrazine is the base. We need this as a concentration, but here, since the volumes are identical for both of these, we're just going to ignore the total volume. So we have 0.006 moles of hydrazine divided by our 0.004 moles of its conjugate acid. So that's equal to 0.006 over 0.004. Okay, so this is equal to 8.48 plus our 0.18. So the pH for the first addition, where we added 20 milliliters of nitric acid, the pH is now 8.66. Okay, on to the next addition. Here we're adding 25 milliliters. So if I have my hydrazine plus H plus, we get the conjugate acid, and we're going to take our 0.01 moles of this that was present initially. We're adding 25 milliliters. So that's going to be 0.005 moles. I got that by taking the 25 milliliters, or 0.025 liters times 0.2 molar. That's 0.005 moles of H+. So then after the reaction, we're going to use up all of this. We're going to use up 0.005 moles of this. So this is 0.005. And here we have created 0.005 moles of the conjugate base. So here, like in the last problem, we have neutralized half of the base that was present. And we have equal amounts of acid and base. We call this the halfway point. At the halfway point, pH equals pKa. Okay, we could go ahead and say that this is plus the log of our base concentration over our acid concentration. But because these are equal to each other, the log of 1 is equal to 0. So this term goes away. So then pH equals pKa. We found pKa earlier as 3.3 times 10 to the minus 9. Negative log of that is 8.48. Okay, so we're at the halfway point now. We've got to keep going here. So in D, we're going to be adding 40 milliliters. So we've got our base, hydrazine, plus H plus from nitric acid, and we get this conjugate acid. So if we have 0.01 moles of this, we're adding 40 milliliters. That's going to be 0.008 moles. 40 milliliters is 0.04 liters times 0.2 is 0.008. So that leaves us with 0.002 moles of this, because 0.01 minus 0.008 is 0.002. And we're also going to be creating 0.008 moles of this. So here we can use the Henderson-Hasselbalch equation again. pH equals pKa plus the log of our base. Our base is hydrazine. And again, technically these would be concentrations, but because the volume is the same for both of these, we're going to ignore the volume component in this. So this is just 0.002 over 0.008. Here we found pKa is still 8.48, and then the log of 0.002 over 0.008 is negative 0.6. So here the pH equals 7.88. Okay, next edition, we're going to be adding 50 milliliters. So let's see where that puts us. So if we're adding, so we got hydrazine, plus H plus yields the conjugate acid. If we're starting with 0.01 moles of this, we're adding 50 milliliters of the 0.2 molar. That's going to be 0.05 times 0.2 is 0.01. All right, so here, after this reaction happens, we're going to use up all of these, and we're going to end up producing 0.01 moles of this. So here we have some of this acid present. So we got to think about what the concentration from the dissociation of this weak acid would be. So we've got H H2NNH3 plus will dissociate into H2NNH2 and H plus. So we're starting with 0.01. Remember, this is moles. We got to think in terms of concentrations now. So we have added a total of 50 milliliters of nitric acid to the 150 milliliters. Excuse me, we added 50 milliliters to the 100 milliliters of hydrazine. So now we have a total of 150 milliliters. So our 0.01 liters or moles, excuse me, divided by our 0.15 liters gives us that concentration, 0.01 over 0.15. This concentration is 0.067 molar. So then we got to figure that to reach equilibrium, if we're starting with this and none of these will have to increase by a factor x. This will decrease by the factor x. So here then, we're going to say that K sub A, which is 3.3 times 10 to the minus 9, equals x squared from our products over 0.067 minus x. But we're going to, again, assume that that minus x factor is really small and just put 0.067 on the bottom. Here we're solving for x. If we multiply both sides by 0.067 and take the square root, we get that x, which is going to be our H plus concentration, is 1.5 times 10 to the minus 5. Let's try that again. Times 10 to the minus 5 molar. So here we can get to the pH by taking negative log of H plus, which is 1.5 times 10 to the minus 5. And that gives us a pH of about 4.82. You'll notice that we added enough of the acid to exactly neutralize the amount of base that was present in our initial solution. This is the equivalence point. So the pH, because we are titrating with a strong acid, is lower than 7 at the equivalence point. That is, again, something that comes up. If we're titrating the other way, where we're titrating a weak acid with a strong base, we find that the pH is greater than 7 at the equivalence point. And here, where we are titrating a weak base with a strong acid, we find that the pH is less than 7 at the equivalence point. All right, so there's one more step to this problem, and that is simply to go ahead and go beyond the equivalence point. So we're adding a total of 100 milliliters. So again, we're taking our hydrazine, reacting it with H plus to form H2N and H3, and and we're starting just like before with 0.01 moles of this. We're adding 100 milliliters, so that's going to be 0.1 liters times our 0.2 molar. So it's going to be 0.02 moles of H plus. We're going to react away all of this. We're going to get some of this. We'll have 0.01 molar again, but we're also going to have H plus in excess, 0.01. The contribution to the pH from this conjugate acid is going to be very small compared to the contribution to pH from just H plus. So we're going to ignore this contribution and just go with finding the pH from this H plus concentration. So pH is equal to this concentration. We got to divide this by the volume, excuse me. So we had 100 milliliters of hydrazine, and we're adding 100 milliliters of nitric acid, so that's a total of 200 milliliters. So it's going to be our 0.01 moles divided by, this is to get H plus concentration, divided by our 0.2 liters. So that's going to be uh, 0.5 or 0.05. All right, so then pH is just negative log of 0.05, which is a pH of 1.3. All right, let me know if you have any questions.